Hello. In this video, we shall discuss generative adversarial networks. It is a very, very important topic of generative AI and completely based on deep learning or deep neural network. So let's start with the basic concept of GAN or generative adversarial network. GAN is not a single network. It is a combination of two neural networks. One is the generator network and another is a discriminative network. The aspects are there is a generative aspects and discriminative aspect. The generative aspect tells that the generative aspect is driven by the genetic models where we try to learn the underlying distribution from which our data set comes from through the variation in autoencoder as an example or through other type of methodology we can generate a new samples from some noisy data or out of nothing the generative model or generator will generate the fake samples or what we can say the fake data. Adversarial means it's a conflicting or there's a competition between two networks. That's why the word adversarial is used. The generator and the discriminator, two different type of neural networks, they compete each other, they conflict each other, and they compete each other. Uh, that's why it is a adversarial, where the generator is trying to maximize the value function, and the discriminator generator will try to minimize the value function, while the discriminator will try to maximize the value function. The generator will generate the fixed samples from the noisy data, whereas the discriminator takes the noisy data as well as the real samples from the real data and performs the binary classification and gives the output, whether the probability, the output in the form of probability, the probability that the output of the discriminator is a real data or not. So that is a discriminator work. We typically knows that discriminator model or discriminative model of that is a driving force of the discriminator is actually based on the conditional probability, where the probability, which is the probability of the target variable given the input variable. Okay, so that is for example that discriminative model of the examples of discriminative models are classification, regression, in regressions, we have linear, nonlinear, logistic regression, binary classification, and other classifications. So the discriminative network or discriminative model or discriminator network that actually makes the different classes of data. They classify the data, or they can predict or they can output some definite value that will discriminate from the other category. So that is a discriminative network. And generative network or generator that creates new data, that creates a new samples from the noisy data or from out of nothing almost. It is creating the new data samples, which are the fake samples always. So that is a generative network. Now the conflict between the generative model and the discriminative model is objected to fill the discriminator the false data to be real. So that is a competition between the generative model and the discriminative model, or the generator or the discriminator, and they compete each other, and they always try to beat each other in a zero, just like obeying the principle of zero sum game, minimax zero sum game. So the word generative is standing for the generative models where the new data samples, fake data samples are generated from noisy data. Adversarial means conflicting. That adversarial word is used to represent the conflict between the generator network and the discriminator network. And the word is used to represent the fact that both the networks, generative and the discriminative, are made by the neural networks. Okay. So it is called generative adversarial networks, that is GAN. What is GAN? What it will discriminate and what it will generate. The generator generates the fake samples from the noisy data. So PZ is a set of Z is a set of noisy data. PZ is a function that passes to the generator and produces the fake samples. And the fake samples is fed into the discriminator, as well as the real data from the real sources is fed into the discriminator. Now, discriminator is to classify whether the data is fake or real. It will find the probability that the data is real. Okay. Typically, if the data is fake, the output should be 0. If the data is real, the output is 1. Typically at the beginning stage. So we have this. Now, whenever the generator's task is to make discriminator feel that the fake data is the real one. To make discriminator feel or to make discriminator conclude that the fake data is the real data. For that, the generator wants to minimize the discrimination of activity. Or we can say the generator minimizes the value function so that the classification boundary will be minimized. The chances of classification between the real data and the fake data is minimized. Or by that way, the discriminator will output the fake data to be real. So that is the motive of the generator, to make the classification process quite bigger, minimize the chances of classification between fake and real. And discriminator will always try to maximize the chances of classification, the probability of classification, or that the probability of classification, whether the data is fake or real. So it will increase the chance of classify whether the data is real, to find the probability that the data is real, or the chances of classification will be more stronger as objected by the discriminator. So the discriminator wants to maximize the chance of classification between fake and real data, while the generator wants to minimize the chance of classification, minimize the discriminator's power of discriminator's capacity of classify the fake or real data. So in this way, this maximization and minimization to conflicting operation actually makes the competition just like minimax zero-sum game. It follows the minimax zero-sum game. And finally at the end, the discriminator will output the fake data to be real. So that is the objective of the generator, and that is the optimal point. Okay. Now, how the discriminator, the neural network is changed, is modified over the time. If the real data is being outputted as real, if the real data, probability of the data is selected, the real data is classified as real, then the discriminator neural network is modified, that there is a change, there's a feedback, and that will change the discriminator network by changing the weights and bias. Those parameters are changed. And also the generator, in the generator neural network, the neural network representing generator, that will also be tried to change by changing the weights and bias, the parameters. Okay, the neural network parameters will be changed to change the generator also, so that slowly the generated data is converging to the real data. So both the neural networks are being updated by updating their weights and bias parameters. so that slowly the generated data as an output of the generator, it it is going closer gradually to the real data. How train again? How to train again? Now this is a mathematical process that that minimax zero sum game between the generator and the discriminator. Okay, and the updation of the discriminator and the generator by updating the weights and bias. That all of the mathematical processes. We will concentrate the mathematical process of this right now in this particular video. We'll concentrate on the mathematical process or mathematical insight between the minimax zero sum game between the generator and discriminator. How to train GAN? First of all, as I already spoken, that already spoke, the generator or generative model of the generator neural network that takes the data from the latent vector or noisy data and generates the image, which is image of data, which is called the fake image or fake data. Similarly, the real data is procured from the real sources of data. Okay. The real training data is given to the discriminator. Okay. And the discriminator will accept both the generated fake samples and the real samples, and it will classify whether the sample is real or fake. It will classify whether the sample is a real or fake or probability of real. It will compute the probability of real. If the probability of real is 0, this means the data is fake. If the probability of real is 1, the output is 1, then this means the output data is a real. So in this way, we have explained the discriminator, the function of the discriminator or discriminative model, and is a binary classifier, or we can say logistic regression is done, or binary classification is done. The matter is same to classify these two classes, classify between these two values, either real or fake. Okay, and outputs either 0 or 1. So it's a binary classifier or logistic regression. It performs a logistic regression discriminator. So now, which network should I train first? Definitely the discriminator network should I train first to maximize the value function. It will maximize the value function, maximize the class boundary, maximize the chances of the fake and real to be classified. Okay, so it will maximize that the fake and real will be classified or will be distinctly identified. After that, the generator will be trained to minimize that particular class, minimize the particular chance of being classified. So that the fake can be felt as real by the discriminator. It will fool the discriminator. So first, the discriminator will be trained to maximize the value function or to maximize the chances of classification between fake and real data, to discriminate between fake and real data. But with what training data? With what training data the discriminator will work? The discriminator is a binary classifier or is a performer logistic regression. The discriminator has two classes, real and fake. It will classify either classify the real data and the fake data, and outputs only one value, that is either 1 and 0. 1 stands for the data, the output is a real, and 0 stands for the output is fake. The data for real class is already given, the training data. The data for real class is already given, the training data, that is the original data, the real data samples, the data of false data for false class that generated from the generator. So that is the noisy data passing through the generator model. It produces a noisy data, it produces a fake data, the fake data samples. Okay, so we are having two types of data. One is the real data samples, another is fake data samples. Real data samples are having some probability distribution of real, and fake data sample is having some probability of distribution of its noise. So the distribution of noise is there for the noisy data, that is converted as a fake data samples by the generator, and there is a distribution of the real data that directly fed to the discriminator. So now we have to train the generator. What is our training objective? The generator will be trained by minimizing the value function, minimizing the discriminator's output. To minimize the discriminator's output, generate images from the generator such that they're classified incorrectly by the discriminator. So the classification will be minimize the chance of classification. It will minimize the chance of classification, or we can say uh, the, the, the classification capacity of the discriminator will be minimized. Classification capacity of the discriminator will be minimized. So what we can say, by this conflict, actually, we should proceed and we'll reach the optimization. And how? First of all, the discriminator is trained. Train the discriminator by fixing the generator with a fixed status of the state of the generator. We are keeping generator fixed. We are in a point, and we'll train the discriminator by maximizing the value function, or maximize the chances of classification, or maximizing the probability of classification, the probability of the data is real. Now the step to the generator is trained to beat the discriminator, to fool the discriminator, to make discriminator feel the fake data to be real. This means it will minimize the chance of classification between the fake and real. Now, it will typically generate images from the generator such that they are classified incorrectly by the discriminator, or the discriminator classifies it as real. Simple. So this is the way we have the bidirectional way. So it will repeatedly, this type of discriminator will maximize, generator will minimize. Then again, discriminator will maximize, then generator. It will repeat it till the optimal point is reached. So we are introducing the mathematical part and the theoretical insight. What are the GANs? GAN is a set of two neural networks. Those are basically used to generate new samples. Initially, those are the fixed samples, and those are gradually changed and modified to match the real data as close as possible. As much as possible, they're trying to make the fixed samples to be resembling to the real data samples. GANs are a class of generative models introduced by Ian Goodfellow in 2014. They consist of two neural networks. We have the generator and the discriminator, and they play the game using the minimax game setting. The generator tries to create realistic data from the fake samples, while the discriminator tries to distinguish real from fake data. Training continues until the generator produces realistic output. So the generator neural network is, as I told earlier, will be modified, will be updated as their parameters are updated, weights and bias are updated. So generator network will continue to update, change, or modify it to match the output, to be match the real data samples, so that it will produce the very closer samples with the real data samples. So now, GAN consists of two models: generator, generate fake data samples, and slowly the generator neural network is modified so that it will gradually generate the samples. The fake samples are modified and transformed into very close to the, gradually closer and closer to the actual data samples or real data samples. And discriminator classifies samples as real or fake. So the generator will actually minimize the chance of classification of the discriminator by generating the data gradually by improving its uh, output, uh, output to match with the real data samples. Now, mathematical formulation. We have the objective function. What is the objective function? Min max. Min G. G means the G function is for generator function that transforms the noisy data into fake data samples. And D, capital D, stands for the discriminator that actually classifies whether the data is fake or real, finds the probability that the data is real. So first of all, the discriminator maximizes this value function V T G. DG, D is the discriminator, G is the generator, and V is the value function consisting of these two neural networks. What is that value function? That is first of all maximized by D, then it will minimize by G, the generator. First maximized by D, then minimized by D, G. In this way, it will go on. What is the value function? We have to understand. Expectation of X. X means the real data. Okay. Real data sampled from, there's a probability, the distribution of the real data. Okay. The X sampled from the distribution of real data. Okay. X sampled from distribution of the real data multiplied by log of the discriminator output of the real data. The probability that the real data is classified as real by the discriminator. Log we are using for scaling, typical scaling purpose. So dx means actually, it's a discriminator function of x, means probability of x, the real data, to be classified as real. So log of dx is multiplied by the x, which is the sample taken from the distribution of the real data, plus the expectation is a average measure, or we can say it is a probabilistic measure. Also we can say it's an average measure. It's the averaging, is a mean estimation of this expression. That is a x, the real samples taken from the real distribution of the real data, multiplied by log of the discriminator probability that the data is the real, plus expectation of the noisy data Z, the noisy data Z taken from the distribution of the noisy data, that PZ. Okay, that is a PG of Z. Actually, PG of Z, that is the distribution of the noisy data multiplied by the log of 1 minus D of GZ. D of GZ means the discriminator output of the generated fake samples to be real. Discriminator function outputs the probability that the G of Z means the generated fake samples, the generated output from the noisy data. Z is a class of noisy data. G is a discriminator function, and G is a discriminator. Okay, that will convert the Z noisy data into GZ. GZ is the fake samples. D of this GZ is the discriminator's output as a probability that GZ is a real data. Okay, so that is a incorrect output done by the discriminator. That is called, that second part is a fake data. Second part represents a fake data. The first part is still with the real data. So expectation that the real data is classified as real, expectation that the fake data is classified as real. Okay. So D of GZ, as I told, the discriminator's probability that the fake data is classified as real. 1 minus of this means the fake data is not classified as real. Okay. Multiplied by the noisy data taken from the distribution of the on the noisy data, Okay, the sample Z is the samples taken from the distribution of the noisy data multiplied by the log of 1 minus T of. So what happens? First of all, the discriminator would maximize this whole value function, is maximizing the whole value function first to make the class boundary stronger. Okay. Then the generator will minimize this. Typically, for minimizing this, it will minimize actually the second term because the first term doesn't have any G. It cannot be changed with respect to G. It cannot be differentiated with respect to G because G is nowhere in the first part of this expression of the value function. The second part of the value function is having the G function. So definitely the G will work in that. So it will minimize on the second term. Okay. So this is a one dimension we are saying. The another dimension we can say that that in the next page we can go training process. Now we are going to find this training process, and in the next part of the mathematical analysis after this sample noise Z from prior distribution PG of Z is a simple printing mistake PG of Z. Okay, so what is happening here is a distribution PZ of Z, that is a distribution of the noisy data. We are taking the sample noise Z. Z is sampled from the distribution of the noisy data. Then generate fixed samples by the capital G generator function. It will generate the fixed samples. Update the discriminator with real and fake data. It will update the discriminator with the classification of real and fake data. The probability that the data is real, the probability value itself classifies the real and fake data. It's a logistic regression or binary classification. Update the generator to fool the discriminator. Then the generator will minimize it, minimize the discriminator's output. So how it happens, the mathematical process. First, the discriminator training. Maximize log of dz for real data and log of 1 minus d of gz for fake data. Why maximize? Because whenever we are maximizing this log of 1 minus d of gz, d of gz means the discriminators, the probability that the output of the discriminator, probability that the output of the discriminator classifies the fake data as real. It identifies the fake data as real. D of GZ means the discriminator's output of the fake data to be real. The probability that the discriminator's output of the fake data, GZ, is real. And 1 minus D of GZ typically means that is a just a complement of that. Okay. The probability that the probability that, of the discriminator's output, uh, probability that a discriminator will classify the fake data to be real, it is not true. This means the probability that a discriminator will not classify the fake data as real. The probability that the discriminator will not classify the fake data to be real, or we can say that discriminator will classify the probability that a discriminator will classify the fake data as fake only. These two things, these two aspects, the real data to be real, fake data to be fake. Okay, these class boundary, this class difference, the difference, these two conflicting terms are being maximized, means it will more strongly classify the real data to be real and more strongly classify the fake data to be fake. Okay, not real. So the classification, the chance of classification is going higher. The probability of classification is going higher in case of discriminated training. A generated training minimize the second part. Second part means the part that deals with the fake data. The second part, log of 1 minus d of gz. It will minimize it. Minimizing this second part typically means, minimizing the second part typically means log of 1 minus d. If I just ignore logarithm for a while, we take 1 minus d of gz. That particular means probability that the discriminator classifies the fake data to be fake, means the probability that the discriminator classifies fake data to be fake is false. Or we can say 1 minus dz means the discriminator, the probability that the discriminator classifies the fake data to be fake. 1 minus d of gz. Again, g of d of z means the probability that a discriminator d classifies gz, the fake samples, as real. 1 minus d of gz means it is not true that the probability that the discriminator will classify the fake data to be real. This means the probability that the discriminator classifies fake data as fake, that will be minimized. This means discriminator will, the generator neural network, the generator part, genetic model will try to minimize, is attempting to minimize the discriminator's classification capacity that the fake data is fake. It is minimizing the chance of discriminator classifying the fake data to be fake. This means it's maximizing the fake data to be real. Okay, so that is the generator's training. Now, we have to use the loss function. The discriminator loss. What is the discriminator loss we have? That's minus expectation of x log dx. Dx means discriminator's output of the real data plus expectation of z, the noisy data. Okay. Expectation of z, that is expectation of x, that is the expectation on the real data, multiplied by the log of d of z, d of x, plus e underscore z means e of z, expectation on the noisy data, multiplied by log of 1 minus d of gz. This is a discriminator loss function. It's a loss function of the discriminator, which we have to maximize. The discriminator will maximize. This is a loss function of the discriminator. This is a gap. Loss function means the gap. The loss function means the gap. Generator loss is LG, we can say, minus expectation of the noisy data into log d of gz. This means itself minus, if I use this minus to bring inside the log, it comes e underscore z of log 1 minus d of gz. So this is a generator loss function. Is a loss function of the generator or the error term of the generator. We have to minimize this one, this term. And here is a loss function, what we have to maximize. By that first part, we have to maximize by the discriminator. Now, min-max optimization. GAN training is a min-max game where G and D compete. Min-max, min G, G will minimize, max D, D will maximize, VDG means value function. Okay. Challenge in training, there are many challenges are there. Mode can be collapsed. Non-convergence can be there. There is no convergence. Vanishing gradients can be there. Gradients can decrease and it can vanish. Training instability, the training output can be unstable. Now the minimax objective function. We are studying ignoring all these limitations, ignoring all these problems. We assume the challenges are not existing and we are smoothly going towards the optimization. By minimax objective function, we are starting. The code training game is defined by VDG, that is a value function, typical value function, expectation of X sampled from the original distribution, real data distribution, into log of discriminators, the probability of discriminators output that the X, the real sample, is classified as real, plus same thing, expectation of the noisy data taken from the distribution of the noisy data, multiplied by the log of 1 minus d of gz. Okay, so that means the log of the probability that the discriminator will classify the fake data as real, or we can say it will classify the fake data as fake. So the sum of these two terms, first part is dealing with the real data, second part is dealing with the fake data, is comprising the total value function. It actually creating the total value function. T aims to maximize the function by distinguishing real versus fake. G aims to minimize this function by fooling T. It will minimize this classification, optimal discriminator. Now, when discriminator is maximizing the function, what we have, it will maximize this value function. Typical condition of maximization, now we are starting the process in detail. The typical condition of maximization is a process of process dealing with the extrema, or we can say maxima or minima. The value function is maximized, means the first order derivative of the value function becomes zero. This means at the maximal point, there is no change of value function if I change the parameter x. So that is the extrema point, either maxima or minima. For maximization, typically it is a maximum. So by extrema rule, we have this first order derivative to be zero. Okay. Now, it follows x sampled from the original data divided by dx, the discriminator's output of the real data, is equal to real data as real. Discriminator probability to output the real data as real is equal to the z samples, okay, sampled from the distribution of the noisy data divided by 1 minus d of the gz. As we have already explained, what is that? The probability that the fake data is not real, or probability that the fake data is fake. So this equation, it comes, okay, by simple algebra from the this thing, from the maximum, from the extrema rule, from the extrema expression, we get the simple equation of this. Then by simple algebraic method, some algebraic procedure, we find out that x sampled from the real data multiplied by dx equal to z sampled from the noisy data multiplied by 1 minus dx. Considering d of g of z equal to d of x. D of g of z means probability that a discriminator classifies the fake as real. We are assuming that probability of the discriminator to classify real as real are same. So we are considering that the discriminator outputs a fake, the probability of the fake to be identified as real, or the probability of real to be classified as real, both are same. This means the fake can be fake and real. There is no difference between, there is no clause boundary. So there is nothing in between. Fake can be classified as real also. Real can be classified as real also. So the fake data can be classified as the actual real data. So this condition tells that. We consider this already happened. By considering this, we create this equation. X divided by dx equal to z divided by 1 minus dx. From that, we find the optimal dx, means optimal discriminator's output in terms of probability that the x is identified as real, x is classified as real. The optimal value of dx, that's the optimal probability that the real is classified as real, is equal to p data, p probability, the distribution of x, distribution of real data divided by distribution of real data plus distribution of fake data. So it is actually probability of distribution of x, means probability that the data is the sample from the x, actually from this distribution of real distribution, what we can say, the distribution of real data divided by distribution of real data plus distribution of fake data. So this is the optimal value of the dx function, dx star. Now putting this value in the value function back, we are putting this value in the value function, we get the optimal value function is minus log 4. By simple algebra and some logarithmic operations, we get it's a minus log 4. That is a value function is optimized is a value function for a value of dx. For a value of dx for which the value function optimized is p underscore data x divided by p underscore data x plus p underscore g of x. So as we considered already that p underscore data x equal to p underscore g of x, this means the real samples and the fake samples, the dimensions are same. We are assuming those samples are same. Okay. The distributions are same. Sample distribution are same. We assume that fake data is transformed into a very, very resembled form of, very, very similar form of, very, very alike form of the real data. So the distribution over the fake data and the distribution over the real data, we assume to be same. So by considering that, we have p underscore data x divided by 2 into p underscore data x. So it is half. So actually d of x becomes half. The probability that the real data is classified as real is now half, 0.5 or 50%. So the 50% probability in the optimal value function, when the discriminator optimizes the value function or maximizes the value function, okay, then the dx, that is the discriminator output of the x, real data, is equal to half. Real data to be real. So the probability that the discriminator will output the real data or will classify the real data as real is half, 0.5 or 50%. There's a 50% chance the real data is classified as real. So definitely the remaining 50% is a discriminator will classify the fake data as real. That is also the probability of that also is 0.5 or we can say 50% at the optimal value function when the discriminator optimizes the value function. The optimal value function's value is minus log 4. And for the dx, for the value of dx for which the value function getting maximized, the value of dx for which the value function getting maximized is half, considering the distribution of the real data and distribution of the fake data are same. Okay. Or we can say, or better to say, that is a d of g of z is equal to d of x because the generated output is close to the real samples. The fake samples are very close to the real samples. So we can replace, we can substitute gz by x in the previous lines. Okay. Considering d of g of z equal to d of x. Considering this means the probability that the discriminator classifies the fake as real is equal to probability of the discriminator classifies real as real. So both are same. When we consider both are same, in that case, this optimal value of dx star, optimal value of dx star equal to half. Optimal value of dx equal to half, or we can say dx star equal to half means probability that the discriminator outputs the real as real is half. This means it implies the probability that the discriminator classifies the fake as real is also 0.5, remaining, that is half. Now the value function tells is the value of the optimal value function minus log 4. Now before examining the minimization performed by the generator, let's have a look on a very, very important divergence function called Jensen-Shannon divergence, or we can say JSD in short. JSD of original distribution and the fake sample distribution, fake data distribution, or noise distribution. Original distribution and the noise distribution, the JSD function tells JSD function is equal to half of expectation of log of 2 into PD divided by PD plus PG. This means data 2 into the real data samples divided by real data samples plus fake data sample plus half into expectation of log of 2 into distribution of the fake data sample divided by distribution of real data plus distribution of fake data. So this is typical, the JSD form in terms of this fake and real data. From here, we can see VDJ. It's very similar to the JST is very similar to the value function. If I look at the value function here, the value function, if I look at in this case, the value function, if I say this VDG is the value function, okay, or we can typically tells the value function to be, we have written already the value function. The value function and the JSD is very close, very similar. So this is the value function, what we have. V of DG is equal to expectation of X sampled from the original distribution of the real data into log of the discriminator's probabilistic output of the real data as real plus expectation of Z sampled from the noisy data multiplied by log the discriminators, the probability that the discriminator will classify the fake as fake. So this is the value function we have. So putting the value to the value function, the value we obtained here, we put in the value function. This is the value function typically we have. The value function typically we have. Just level loop. This is the value function again. This is the value function in the second line, what we can see. We typically put this value in the value function. Now, we typically compare this JSD with the value function. We find that value function is 2 into JSD. You can find in the RAF. You can examine, you can test it also. 2 into JSD is a linear function of JSD. It's very close, same form, except it is multiplied by 2 minus 2 log 2. So something constant to be multiplied with JSD minus a constant value will give us the value function. So typically the value function equal to 2 into JSD, Jensen-Shannon divergence, into minus 2 log 2. So if you just compare these two, this expression comes. Is equal to what? Simplify, we can write 2 into JSD minus log 4. Our analysis becomes very, very easy and simple now. Because we know JSD by abstracting the JSD whole mathematical function by just the word JSD, it will become, the whole process will become simpler. Now the generator minimizes. The generator's effective objective is to minimize the value function. The value function we are left with 2 into JSD minus log 4. We have already got it. In the second line, you can say the value function which is already maximized by D star, that is there's an optimal discriminator value, also optimal discriminator value for which the value function is maximum. Okay. We are minimizing this particular form. That is a 2 into JSD minus log 4. That is the total value function we are minimizing. This is a total value function what we are minimizing. G cannot minimize log 4 as log 4 is constant. So G can minimize only JSD, the Jensen-Shannon divergence function of the real data samples between the real data samples and the fake data samples. Okay. So it will minimize it, JSD. As we see the JSD form, the form of JSD you can find, since it's a logarithmic expectation, the expectation of the logarithmic value. So it cannot be negative ever, can never be negative. The minimum value of it should be 0. Any logarithmic function, the minimum value should be 0. It cannot be negative. So the generator tries to minimize the value function, and the value function means generator actually tend to minimize JSD, and the minimal value of JSD is 0. Minimal value of JSD is 0. As minimum value of JSD is 0, we are left with the optimal value function equal to minus log 4 after the generator minimizes it. Minus log 4 will remain intact. Minus log 4 will remain intact. And 2 into JSD, that part will become 0 because JSD we are making 0 as minimized. We assume that the generator minimizes completely, so JSD becomes 0. If JSD becomes 0, it will become log 4. Okay. And JSD becomes 0. JSD becomes 0. Just see the JSD formula. we are making the minimization of JSD to be zero. When the JSD is zero, if the PD is equal to PG, P underscore D equal to P underscore G, then only the JSD will become zero. Typically, JSD will become zero when we have PD and PG are same. Okay. So we have PG and P data are same, perfectly match distribution. Those distribution of the fake samples and the distribution of the actual data samples are same. They perfectly match. Then only we can say JSD is minimized and discriminator just minimizes JSD. Actually, they are matching these fake data samples and the real data samples. And as we know, internally, it can be possible by changing the weights and bias. The generator neural network is modified. It gets better. It's getting updated with its updated weights and bias. And by updating gradually, it takes the fake samples generated by it to be very close to the data so that distributions are almost same. Whenever distributions are almost same, the JSD function will become zero and the value function is left with minus log 4 again. So after the discriminator maximizes the value functions, maximus value is minus log 4. After the, again, when the generator minimizes, again the minimized value function is equal to minus log 4. It will produce the same value. So the value function will give the same value. And that is happened because of, we have assumed, we have already set this equality that distribution of the fake data is equal to distribution of real data. So the fake data is transformed into the real data. Then only this value function maximization and minimization is possible. So we have practical training losses. We have almost described the process successfully. We have the discriminator loss function. We have generator loss function. Avoid vanishing gradients and stabilize training. So we have the step-by-step method. First, sample mini-batch real data. Okay. Sample the noisy data. Okay. Noisy data and transformed by the G function. One step is not written, but it is true. It should be written. It can be written as a third step that the sample noise is taken. And then we have the G generator function, the generator neural network, through which these sample noises are passed and the output is a generated output, or we can say fixed samples. After that, we update D by using gradient accent because we are the discriminator D is maximizing the value function. So definitely gradient accent will be used. Okay, gradient accent means the value is increasing gradually. So the value function's value is increasing gradually. So we can write in this way. The value function's value is increasing gradually. Okay, that is in simple form 1 by n, that is averaging in the place of expectation. Theta d is the parameter. Okay, the parameters are changed, the gradients are changed, the gradient accent thing, the parameters are changed so that the value function becomes higher and higher gradually. It reaches its maximum. Okay, so 1 by m summation of this whole thing is there. Okay, so there's a value function. Update G using gradient descent. Now G will take the second part of the value function that tells the discriminator's output of the fake data. It will minimize that. It will minimize the chance that discriminator classifies the fake data to be fake. Okay, classifies the fake data to be fake. It will minimize by gradient descent. So as it minimizes this one, we have to write update G using this function. Log of G of 1 by m is averaging. Theta G is the parameter weights are bias combined. Generally, we can say theta underscore G is the generator circuit in the generator network multiplied by log of D of GZ. Log of D of GZ means we have already got it, GZI for ith sample. Okay, for ith data. What we can say, the probability that a discriminator classifies the fake to be real Discriminator classifies the fake to be real. Okay. So that should be the motive by which the G will be updated. G will be updated by changing weights and weights. By changing the weights, okay, new weight equal to old weight minus the gradient of the loss function. As we know, the very well-known deep learning method. So G is updated using the gradient descent. Updated using the gradient descent, and the average value, it will work with the derivative of this one with respect to the weight. So we have 1 by m, that's the average, substitute of the expectation, summation of log of d, z, dg of z. This means the probability that a discriminator will classify the fake as real. Okay, fake as real. We are making the log of that for scaling. The sum of all data points, it is applied, that's a summation. 1 by m is the averaging. So we are updating G using the gradient descent. We are updating the G because G minimizing the function in this way. Okay. And for minimizing the function, we are up by changing the neural network by weights and bias. G is the neural network, generative network that is having the weights and bias, that accepts the weights and bias, that changes the weights and bias. Okay. By changing the weights and bias, okay, new weight equal to old weight minus weight gradient. So we have this, the gradient descent. By using the gradient descent, this is a gradient by which the G is updated. Okay. Key mathematical components are used. And thank you so much. In the next video, we will discuss the Python algorithmic representation of the GAN in a comprehensive way and the Python code implementation as well. Thank you.